topic about the natural hydrogen, a geologic curiosity or a game changer for the energy transition. Our vision is to be open, sharing information with our peers across the company so we can provide energy to the kingdom and of course meet many new faces, and we also like to see smile on your face. For the announcement today, we have 843 total members with 397 students and 448 professional members. And with some labs, about 91 members, please renew your membership. And every year, we run an SPE scholarship program for our SPE student member in Thailand. We basically run a mini competition requesting students to provide their motivation while they think
SPE program share. I'll do the usual introduction of the speaker, so by reading his bio. Okay, so our speaker tonight, he has 40 years experience in the energy resources sectors, initially working for Shell and then at the Atlantic Richfield.
All right, good evening, everyone. My name is Kasi, and I'm the SPE program chair. I'll do the usual introduction.
He left Big Oil in 2000 and co-founded PDA Limited, which is in 2004 became Serica Energy PLC, which today is the sixth largest producer of oil and gas in the UK North Sea. From 2006 to 2016, he went on to build and finance numerous other successfully E&P startup companies, which all of which were either successful IPO or trade sold to major international oil and gas companies. In 2018, he co-founded Helios Aragon, which is the exploring for natural or gold, hydrogen, helium gas in Spain, Poland, and other countries. He currently acts as the non-executive director of Rex International Holding in Singapore and as a board member for their subsidiary company Lam Petroleum in Norway and Masira Oil in Oman. In 2020, he was elected to the board of Far East Gold, which is an eco-focused miner exploring for gold and copper in Indonesia. Our speaker has a highly successful track record of building and financing startup energy and resources venture with multifold returns to the stakeholders. He is a past president and life member of SEAPEX and spent many years in the early 90s as active council member of the Indonesian Petroleum Associations. Our speaker holds the BSc and PhD in Geology from the University of Wales, UK. Ladies and gentlemen, please join me for a warm welcome. Our speaker finally. Dr. Chris Atkinson, the chairman of Helios Aragon, correct? Thank you.
Well, it's very nice to be here tonight. It's a long time since I've been in Bangkok. So in terms of work, probably nearly 20 years. It's great to see a large number of people here, hopefully eager to understand something about natural geologic hydrogen. Going. I'd like to tell the students at the back of the room, please try and follow this talk. There's going to be some prizes given away at the end from Helios. One per table, one for the geologic table and one for the engineering table. Two questions at the end, specifically for the students. As I've just mentioned, I'm the chairman of Helios Aragon. Helios Aragon is funded and originated in Singapore. And we have operations in several countries, but our main centre of operation is in Madrid, and then an opportunity in Spain, which I'm going to talk to you about later. Now, for everybody in the room, unless you've been, I think, living under a stone or in a cave, there is this thing called energy transition, which is apparently taking place. And there's a lot of talk about the role of hydrogen in energy transition. This slide is taken from Reichstad, therefore it must be correct, since they produce lots of graphs and lots of numbers. And this is a view of what the energy is going to look like in 40 to 80 years time. Key figures is hydrogen from solar, wind, hydro, geothermal is going to be created. It's called green hydrogen. I'll talk about that shortly. That's going to be doing a lot of work to generate electricity or to store energy to provide electricity. And you're going to see at the bottom there that natural gas and oil is going to have smaller and smaller roles. Right now, the world uses just over 70 million tons of hydrogen. The projection is that not 40 or 50, 80, but in 30 years' time, we're going to need 500 million tons, okay, per year. So we're at 70 at the moment. And of that 70 million tons, most of it is produced from natural gas, 71%. And that equates to around about 8 TCF per year of gas, which is converted into hydrogen. And for people who don't know the main uses of hydrogen, well, we're in the oil and gas business, we should know the biggest users of hydrogen are our refineries. Hydrogen is a very, very core product, very important in refining. And the second important use is in the fertilizer industry. But that's currently. In the future, we're going to try and use it to power things. And because of this, and because of this huge demand, there's a lot of interest in hydrogen. And I'm talking here specifically green, grey, whatever colours you want, but mainly green hydrogen. There's a lot of projects that have been sanctioned. And this is from the Hydrogen Council and McKinsey, so it must be right, 2023, where you see that there are over 1,000 projects that are scheduled to take place. And this is basically green hydrogen projects. The majority in Europe, Latin America. And if you look to the far right, you'll see where we are. There's not many in this region, but there are some. But it's basically big business. And you can see here how that's going to happen. This is a projection through to 2030. Renewable hydrogen is going to ramp up. I love these graphs for energy transition because we're always down on the left-hand side, and there's always these beautiful hockey sticks showing we're going to go up here. But this is what people believe is going to take place. But it's a huge amount of hydrogen, and it's going to have to come from somewhere. So for people who are not familiar, if you do look and listen to people talking about hydrogen, they will talk about the hydrogen rainbow. And hydrogen is classified in a series of colors, depending upon how it's manufactured. And by far, the biggest producer of hydrogen, I mentioned it earlier, is what we call grey hydrogen, which is using steam methane reforming, either from methane or from coal. That's the biggest producer of hydrogen at the moment. Blue uses the same as above, but you have some carbon capture, so you actually help the planet a little bit, and by storing the carbon. The real panacea is green, which of course just uses renewable electricity to run electrolyzers and to make hydrogen and oxygen from water. And then you have a turquoise variety, which is sort of like grey, but it doesn't involve actually burning. It's just a pyrolysis treatment. It's a chemical reaction, and that's called turquoise, and it's a byproduct. It's again uses natural gas as a feedstock. But the one I want to talk about today is the last one, and the one that hopefully people in the room, you're all excited to hear. It's either called gold hydrogen if you're in Australia, or if you're in the UK. If you're in France and Germany and other countries in Europe, it's called white hydrogen. But essentially it's the same. And it's natural hydrogen which is generated within the Earth. Now, on the left here, back in 2020, during lockdown, I had very little to do, stranded in a bedroom in Singapore. And I thought, well, I'll go into Google and say, does natural hydrogen exist? And in 2020, Google told me no. Well, that's interesting, because we found lots of hydrogen in the world, but Google hadn't obviously bothered to look and see it. So does natural hydrogen exist? No is the answer. You can read in the box below. It doesn't exist naturally on Earth, since it forms covalent compounds, most of the Earth is in, so there's no molecular-free hydrogen. And so if you've got an existing prejudice which implies natural hydrogen doesn't exist, no one's really going to look for it. The gods have spoken. It doesn't exist. Why are you looking for it? Of course, being the lightest of all gases, by the way, it's the only gas that can escape the Earth's gravitational field. If it does come to the surface, it dissipates, and it's very, very hard to measure. In fact, we don't even monitor for the presence of hydrogen in air. That's how the fact that people just don't think it's there. Hydrogen is rapidly consumed also by microorganisms. It's a great source of energy. It gets gobbled up very, very quickly. And so natural hydrogen is really still poorly understood. But what I want to tell you is that things are changing, and they're changing rapidly. These are, on the left, the graph at the left is just showing the number of publications with regards to natural or geologic hydrogen. And you can see, again, a nice hockey stick. It's ramped up since about 2018. So there's lots of activity. And then you're going to see a series of either reports from conferences or special volumes which have been put together by the Geological Society of London. Natural hydrogen, the new frontier. USGS is in on this. They've got a huge project now looking at natural hydrogen. Even the New York Times, in the top right-hand corner, is this a gold mine for clean energy that's hiding right below our feet? Everyone now is starting to actually think about it and look about it and try to understand. Now, in terms of global occurrences of natural hydrogen, this is why the Google thing always sort of shocked me. We've known that natural hydrogen exists for a long time. In fact, 200 years ago, the Spanish discovered in the Philippines Los Fuegos Eternos, which is a series of fires that continue to burn. And those fires are 42% hydrogen. So we've known about it for a long time. We can even go back further. But the main point out, there's hundreds of global occurrences of natural hydrogen. This is a map of the world. It's in French. It was modified by a French person, Rigolet, from the real guru, the man who you'll see shortly. If you want to understand natural hydrogen, you have to read this paper. It's an Earth Science Review paper. It's about 80 pages long, and it's about 100 pages of tables and references. And it's by a guy called Slava Zonik, who's Ukrainian. And the good thing about him is that he can speak Russian, because the majority of work on this subject is in Russian in the early days and was actually pioneered by the former Soviet Union. But the most important thing to see, these are real occurrences of natural hydrogen, and you'll see that there's a lot of natural hydrogen in the mid-oceanic ridges. lots of heat, lots of water, which is useful for that formation. You'll also see that it's in cratons in the orange blobs there, generally failed rifts, and also it's linked to ophiolites, rocks which are rich in iron. There's one dot there, which I'm not sure if I can. How do I point? Can I point with this? There's one dot there in Mali, and that's the only commercial operating hydrogen project in the world currently. But there is one. And that one produces at 98% purity, a shallow depth. It sources hydrogen to a local power station. It's merely just burnt. And 12 wells and a field area of about 50 square kilometers. So this actually exists. In Iceland, you probably know that it's got enormous geothermal power. And that plant emits about 1.2 kilotons of hydrogen per year. A lot of hydrogen coming along the mid-oceanic ridges. And there's exploration drilling going to take place. There's actually wells already been drilled in the United States. There's a well drilling right now on the York Peninsula in Australia. It was press released today to have found natural hydrogen, and they were re-drilling a well from 1931. And I'll talk to you later. We plan to drill a well in Spain in 2024. And the other thing is that when you go and find hydrogen, you often see that when you locate its seepage at the surface, it's often associated with these features here, which are small, well, not small, they're quite large, semicircular depressions called fairy circles. And they're often indicative of where natural hydrogen is seeping. It causes a problem with the vegetation, and you get these weird patterns, and they're generally circular. So we know this is good. The other thing is that the oil and gas industry has been quite active, of course. You know, we drill lots of wells. We don't necessarily drill wells where you'd expect to find hydrogen. But when we do drill wells, we often find hydrogen. And here's some examples. This is a well in Denmark on the top left that had 16% hydrogen in the gas. There's an Australian well, very famous one, Mount Kitty. This one will be re-drilled, hopefully within the next couple of years. That's 11% hydrogen, 9% helium. Ukraine, in the bottom left, 44% hydrogen, Belarus, 24%. As I said, the former Soviet Union is where you need to look for information on natural hydrogen. And on the right is Mali, and the one I mentioned earlier. So, to give a quick overview, natural hydrogen, it's generated within the Earth by a variety of geological processes. We're going to talk about those shortly. It can migrate and hopefully accumulate in large deposits. It's supposed to be, I think, starting to be recognized to have potential to revolutionize the clean energy transition. It's the lowest cost, and this is really important, the lowest carbon footprint source of hydrogen. Okay, if you don't believe me, you can talk to me later. Studies recently been conducted by Stanford University, which nails this pretty well. Provided you've got more than 60% hydrogen, you've got the cleanest hydrogen in the world. No new technology, of course, is needed. Look at this room. We're surrounded with people who've got enormous talents. This talent is easily transferable to this business. Nothing new here. This is just old ideas in completely new areas. And the big problem, and I was just sitting on the table talking earlier, is legislation. Most governments in the world do not have legislation for natural hydrogen. They've never bothered with it. It doesn't exist. And it's a real problem because it generally, what we're seeing is that it falls between either the petroleum law or the mining law, depending upon how you look at hydrogen. It's the only thing, I think, at the moment that's stopping more activity. But, and so far, only France and 2 states in Australia actually have legislation for the exploitation and a fiscal regime designed around natural hydrogen. So, probably more important to the geologist, where would you go and look for it? Well, ultramafic rocks are apparently pretty key, especially ophiolites, and these are rocks that are rich actually in minerals which are iron rich. And in terms of ophiolites, it's very important that they are serpentinized. The process of serpentinization, chemical reaction, generates hydrogen. It's part of the reaction. Iron-rich formations, again, presence of iron, very important. It's been noted within coals and coal-bearing basins. There's a very large project in Alsace in France, which is looking at this at the moment. Salt and in particular potassium-bearing salts. This is coming from the Soviet Union. They found a lot of linkage between radiolysis of water trapped in evaporites and the presence of hydrogen gas. It's also been known about for years in fault zones. I worked with ARCO in California, and people used to measure hydrogen on the San Andreas Fault, and you knew if you saw a peak in hydrogen, the fault was about to go. And in fact, that work now is starting again in many areas, but cataclasis is important. It probably doesn't generate a lot of hydrogen. And then you can see down to the bottom to geothermal as well. This is the paper that if you're interested, you all need to read. It's in English, and like I said, has large amounts of references. And I'd say that Slava is really the guru of natural hydrogen. Just to sort of summarize or to talk about it in a little bit more detail. So there are really 4 ways that you can generate natural hydrogen. The first 2 on the left both require the presence of water. That's a key ingredient. One is serpentinization, alteration of ferromagnesian rocks, rich in iron, and you generate the hydrogen from oxidation reduction of the water, which combines. There's a big project which is scheduled to go ahead in Oman, which is going to be actually injecting water and CO2 into the Oman ophiolite, and to see if they can actually generate hydrogen. Second is radiolysis, but radiolysis, you're basically using radioactivity, natural radioactivity, to react with water and do the same thing that electrolysis is doing with wind and with solar power. But you're doing that inside the earth. Rock crushing, I've already mentioned. The last one here, degassing, is a bit contentious. I'd like to talk about it, and if people ask at the end, I've got a slide to explain it. This is the parallel universe for how the Earth originated and what is the composition of the Earth. You must remember that in the Western world, we view the Earth to have a solid iron-nickel core, and we view it to have a molten iron-nickel outer core. There are people who will dispute that, and scientists, especially in Russia and the former Soviet Union, who have a different theory about the evolution and origin of the Earth, which perhaps should be relooked at. So how do you, in terms of hydrogen system, let's try and look at this in terms of how it connects or how it looks by comparison to an oil and gas system. So on the left of this diagram here, and this, by the way, is from Jackson, Owen Jackson, from a company called H2O. It's quite cute, isn't it? Gold hydrogen. But on the left-hand side, Owen has shown that, with methane, what do? We get a source rock, we bury it in a basin, we heat it up a little bit, 160, 200 degrees centigrade, and we don't need any water, but over millions of years, through catagenesis, we form oil, and ultimately we form gas. If you then use the same ideas with hydrogen, and let's just concentrate on 2, serpentinization and radiolysis, and serpentinization is perhaps the most important. In this case, the big difference is the rate of this reaction is measured in hundreds of years, not millions of years. So when I was in the Philippines, I was asked a question, actually by one of the universities, is natural hydrogen sustainable? Well, if you're producing it from serpentinization and you're quite willing to accept that 100 years isn't that long, it is sustainable, because it takes about 100 years to do this reaction. But you need a much higher temperature, and you need these iron-rich olivines, especially dunite. Now, in the case of radiolysis, actually it takes a lot longer. I've said billions here. I really mean hundreds of millions, not billions. But in these cases, you need water. And in this case, you just need uranium, thorium. You need a source of radioactivity. So similar but different. Now this is the one that always freaks people out, because hydrogen is a very small molecule. How can it possibly be trapped in the earth? It just disappears. Well, that's not actually what the science and the data says, because people have actually looked at this, and they've actually looked at the trapping of hydrogen and compared it to methane. And there are two studies here. This is one, this is one from the H2O guys again, Jackson. And I apologize, this is quite small, but this is, this is capillary entry pressure data. I hope everybody's familiar with that, and you can use that to work out seal capacity. Everybody should be doing it anyway. Don't leave it to the computer. But if you go and measure these things, you'll see that when you look at the hydrogen, and another thing to remember about hydrogen is it's insoluble in water, unless you're at very, very great depths. So if you have water in your shale, the hydrogen will find it very difficult to get into the water and diffuse and disappear. It's going to behave like a gas. And so when you look at this, you'll see that people have looked at the various contrasts between methane and hydrogen, and they're almost the same. And in another study here, which is actually on real rocks, was done in the University of South Australia, then again a similar result. That's the difference in seal capacity between methane and hydrogen is almost identical. So what this means, and this is important because you'll see a lot in the literature, that to trap hydrogen you need hundreds of meters of salt or halite. Actually, you can probably do it with pretty good shale, but the shale has to be, reasonably good. Now, one of the things to think about with hydrogen is losses, because it is a dynamic gas and it is an energy source. Then once it gets quite shallow in the earth, lots of creatures, more so than, say, biodegradation of oil and gas, hydrogen is very easily attacked by microorganisms and can be eaten up. And so you have to bear in mind that there is this reactive losses that can take place. And it's limited to the zone where hydrogen is in contact with water. But it's just a slight difference. You do get reactions in oil and gas compared to hydrogen, but hydrogen is worse. And I like this. This is a nice summary diagram from Science. And by the way, earlier I mentioned Zonic's article. If you just want to have a nice simple read to understand about natural hydrogen, the article in Science in 2023 is very, very good. It's good science. It explains it. And this is a summary diagram just showing on the left there the Earth's hydrogen factories. I sort of like it because you can see that we're in an energy transition, slightly green world, because in terms of extraction, there's only one dot here, 8, which is actually using technology that we know to drill down and actually extract it. But it's basically summarizing how the hydrogen system works and how it's thought to work, from generation on the left, as I talked about, radiolysis, serpentinization. But they do mention deep-seated, this idea that we talked about, the Russian idea, which I say I can talk about later. And then it's talking about loss mechanisms. It can escape very, very easily. You need to have a good seal. In this case, it talks about the presence of salt, and then how you can actually access it by looking in the subsurface. So exploration strategy, you should really focus on areas where you have ferrous iron or natural radioactivity. Mafic mantle-derived rocks or rocks rich in iron, banded ironstone formations. That's key in places like Australia and in Africa. Appear to be very important as potential source rocks. Ophiolites definitely seem to work, and there's lots of examples of that. And a commercial accumulation, just like oil and gas, requires source, migration, a reservoir, and a trap. So again, this is stuff that people in this room, we know a lot about, and we can apply a lot of this to trying to find natural hydrogen. And the last point there, accumulations are more likely to be found below salt, and I think that's probably right. But as I mentioned earlier, they can be below shale as well. And in the case of Mali, they're producing, their shallowest hydrogen is being produced from 600 meters, and the seal is a doleritic sill. Now that's because the hydrogen is being generated almost right now, but a lot of it. And by the way, that field has been on production and there's no pressure depletion. So it's constantly being, recharged. They don't produce a lot, mind you. So to summarize a hydrogen system versus a petroleum system, I suppose the one big difference in a hydrogen system, the source is more than likely going to be outside the basin. It's cratonic generally. And that the source of the hydrogen finds its way into, shall we say, a sedimentary basin through faults or through various other, fractures. In contrast to a petroleum system where the source rock sits inside the basin and it's the organic rich area. So there is slight difference. But after that, they're pretty much similar. The only thing is that hydrogen, as you get close to the surface, tends to have greater diffusion. But, there's a lot of stuff that we can take from oil and gas exploration and bring it to bear on this problem. The other thing, of course, is the different temperature windows. Hydrogen, 200, 350, is certainly the case of the serpentinization reaction, and it's a little cooler when you're in oil and gas territory. Okay. I'm now going to just switch attention to our project in Aragon to give you an example of a real project. I don't know if anybody's been to Spain. I don't have a map of Spain, but Spain sits on the Iberian Peninsula. It composes most of it, and it's separated from France by these snow-capped mountains here, the Pyrenees. So this part of Aragon is in this province of Aragon is in northern Spain. This is the town of Monzon, and this is the citadel, which sits on a very nice exposure actually of a Oligomycete molasse. And the Monzon 1 well was drilled by a company, a local, actually a Spanish national company called Empasa in 1963, and it was drilled to explore for oil and gas. There was a huge effort in Europe at this time to drill for oil and gas, and most countries, if they had any budget or areas, there was technology available, and off they did, and they went and drilled wells. And they often drilled wells in places which probably they shouldn't have done, and if they were looking for oil and gas. And you could say that this may have been one area. No hydrocarbons were encountered in the well, but it had very high levels of hydrogen. And there were other wells drilled at the same time in this campaign in a similar area, which also had hydrogen. 1963, hydrogen was basically a dry hole, and this well was basically plugged and abandoned without testing, despite seeing gas presence on the logs, and was just forgotten about. And but if you look at the area, and we've studied it quite a lot, that all the elements are present in this area for large-scale accumulations of natural hydrogen. There's a source coming from very deep-seated faults which connect to the orogenic belt. There's reservoirs, there's traps, and there's lots of seals at this particular level. And we think anyway, and I think it's pretty true, that this is the first documented example in Europe of a complete hydrogen system. Just a stick plot of the well. This is the Monzon 1 well here. This is surface, and the well TD'd. It's about 3,715 meters. It didn't TD in basement, but it was very close to basement. And it was in fact in a quartz pebble-rich conglomerate of Triassic age. And the succession, as you look in the well, there's this there's a very thick sequence of very young tertiary molasse. Salts. There's a very thick sequence of halites, which are tertiary in age. You then have a major unconformity where you jump from the tertiary to the lowermost Jurassic. And then you have a fairly conventional sequence of upper, middle, and lower Jurassic and Triassic. People who are familiar with the geology of Europe will know this. It's the threefold division of the Triassic. It occurs across most of Western Europe and into North Africa. And well, what was interesting was that there were 2 intervals in this well, which are indicated by the green triangles, where you saw, or the mud logging and the logging and the well site geologists picked up the presence of hydrogen. One fairly shallow, and a very, very important one right down at the bottom here in the Bunter sandstone. And just to give you a summary in terms of the system itself, the Bunter sandstone at the bottom there is about 55 meters thick, and overlying that vertically in this well, there is something like over 1.7 kilometers of excellent sealing lithologies above the Bunter. There's intervals, there's the Rot halite, there's evaporite-bearing Bunter shale, there's halites up in the uppermost Triassic, and there's 1,000 meters of halite here, up in the Tertiary. So you've got a lot of potential seals which sit above where the hydrogen was seen. This is a little bit more detail on the shows. This is the shallow show, 410 to 487 in the Tertiary, 0.4 to 1.2 total gas. And these shows were determined by a Prackler detector to be pure hydrogen. And I doubt if anybody in this room knows what a Prackler detector is. No? Good, because that was me just a short while ago, back in July. I didn't know what it was either, but I'm going to tell you. The second show, which is the most important one, is down here in the Bunter, 3,600. It was a 25% total gas show, which was determined by the Prackler to be pure hydrogen, and that's the thing that I suppose gets you excited. This well, by the way, had some methane. It had some other things in other formations, little traces. So we think the equipment was working quite well, but this one was the big one down here. Okay. So if I'd have given this talk 6 months ago, I couldn't have told you what this is. But these wells in this part of Spain didn't use a gas chromatograph. The rigs were American rigs, but the well site equipment was provided by a German service company called Prackler, who I think if anybody's a geophysicist and old enough, you'll know that that was a forerunner to Gico Prackler, because they were very good at shooting seismic. But they also had other technologies, and one was a mud gas detection system. And this is from their pamphlet in 1959 advertising their services. And the difference is that this isn't a gas chromatograph. It's actually a modified ORSAT gas analysis system. And the ORSAT apparatus is still used today. It's a key way that you measure the composition of flue gases in furnaces. And it differs from a gas chromatograph in that it gives direct measurement of up to about 5 or 6 gases. And importantly, it gives a direct measurement of hydrogen because it uses a platinum catalyst to react. And so you have a definite presence of hydrogen. So this was a real important thing for us because we were trying to work out what type of gas chromatograph they were using, how could they see hydrogen, if they were using hydrogen as a chase gas into the equipment, using hydrogen to calibrate the equipment. Well, didn't need to bother because they didn't do that, they used something else. To illustrate this problem, this is a gas chromatograph response of hydrogen. This caused huge consternation when this well was drilled. I won't tell you where the well is because it's quite important. They had a giant gas kick. You can see it's not just over a small interval; it's over quite a large interval. And there was no separation in the readout of the standard X-log chromatograph between methane and hydrogen. However, hydrogen gives around half the response. The main thing was that this perplexed the operator. They thought their equipment wasn't working correctly. X-log came in and did a really thorough job trying to work out. They worked out, first of all, their equipment was working. They looked at it, and the only conclusion they could make was that this was actually hydrogen, that the extra hydrogen had come into the mud during the drilling of this formation. And we now know that's correct. But it is a problem, and it's a big problem. So if you think about a lot of the wells that have been drilled, certainly from the mid-60s onwards, and you're using gas chromatograph, it's going to be very hard to even know if there was hydrogen in the well. So that's an important thing to realize. Just going back to Monzon, the reason we sort of like this a lot is that I told you at the beginning, logs were ran in the well. There wasn't a sophisticated log suite, but there was important logs, in particular the neutron. Neutron is an important log for hydrogen. The petrophysical analysis shows that there was reservoir quality in the bunter, and importantly, there was gas. There was some sort of gas over the bunter interval, and you can see here on the you can see here on the cross plot there's gas effect, and our internal work on the well confirms the presence of reservoir, confirms that there was a substantial zone of high gas saturation. And the net result was of the 55 meters of bunter, there's around about 30 meters of net pay, around about 9.5% porosity. Average water saturation, which, you know, given the errors that you can make, is around about 36%. But the general view is that there was gas in this well. And of course, the only instrument we have is the ORSAT measurements that this was natural hydrogen. So we believe Monzon 1 to be a hydrogen discovery. This is a tiny little postage stamp. That's a top structure map. The Monzon structure was drilled originally on 2D and gravity data. These are big features. Monzon A, which is what you see here. The red is around about, in methane terms, around about a 500 BCF recoverable prospect. B and C take it up to about 2 TCF. It's a big basement high. So we believe that there's certainly a source there. And by the way, we have gone back and done surface geochemistry, a detailed surface geochemistry study. And there's an old chap sitting here on the table on the right who actually went out there and collected some samples. And we were able to show that there was a huge anomaly for hydrogen and helium right over the old well, which there should be, because the well has punctured its way all the way down through all those seals, and it's gone down to the level of the bunter. It's big news in Spain. The local government, or in particular the regional governments and the provincial governments, are very keen to see this developed further, and it's Helios's plan to basically re-drill the Monzon 1 well, probably in about a year's time, once we get all the final permissions. Now, just going back to natural hydrogen and the world we live in, and I don't know if you're all familiar with when you go into the energy transition and you talk about new technologies. People deal with the TRL, the technology readiness level. Now, I was completely dumbfounded by that, but you know, you've got to come up with an idea, you've got to prove it, you've got to demonstrate it, then you've got to go and do a small-scale prototype. You've got to do all this. This is all designed around, say, for instance, green hydrogen or something like that. And then Gauthier and some of the French co-workers have taken that and just said, well, where are we with native hydrogen exploration? Well, you know, a lot of the energy transition projects are up here, you know. They're an idea with a little prototype that's taken 20 years. With natural hydrogen, we're actually already down here. You know, and in fact, if you think that Mali is actually a proper working, we're actually a bit further down here. So in terms of accessing funding in this current climate to do work like this, you've got to have a high TRL score. And it needs to be, you know, north of or higher than 5. And natural hydrogen is pretty much a 6, 7, 8 already. And there's going to be, like I said, wells drilled that are going to move it into 8 and then hopefully into 9. Now, one thing I will say, and there's people old enough in the room to remember this, 20 years ago, we were actually here. And we were going to go off and look for natural hydrogen. And there's a very famous paper written by Smith, who's a British Geological Survey, in 2002. And you can read it for yourself. But, you You know, in 2002, in recent years, a number of magazine newspaper articles have been written predicting the imminent replacement of hydrocarbon source fuels by hydrogen gas or by hybrid fuels containing hydrogen. Hydrogen is especially envisaged as useful for transport purposes and the hydrogen economy. And And the key thing is in that paper, Smith outlined a lot of things I think now that we've been able to follow up on and done more work to substantiate. But, you know, it was written down then. I don't know how much natural hydrogen can be discovered, but there is enough evidence to justify a search. And that's what we should be doing. And that's the message I'd like to leave with you tonight. Now, just some conclusions. Hydrogen is the most energy rich of all natural gases. I had a question on that in Manila, but I was talking with an engineer, we eventually worked it out, and I think that statement still stands. Synthetic production of sustainable hydrogen is expensive and grossly inefficient to compete with fossil fuels, and we all know that. It's much cheaper to use SMR, and you can manufacture hydrogen for about $2 to $3 a kilo. Natural hydrogen in Mali is around about 50 cents a kilo. The Spanish project I've talked to you is about 50 cents a kilo. And green hydrogen in Spain is 22 euros a kilo without government subsidy. Exploration for natural hydrogen is a lower cost and a smaller carbon footprint than green. That's a fact. And could this make hydrogen a source rather than a vector of energy change? And I think what we've got to remember is exploration for natural hydrogen is in its infancy. And you really do need to think that we are pretty much where oil and gas was shortly after Drake probably drilled the first well. There's not many wells that have specifically gone out and drilled for natural hydrogen, certainly in the Western world. And natural hydrogen is a carbon-free, sustainable resource, constantly being generated by geological processes, which have likely been active since primordial times and will continue for millions of years to the future. And at the bottom there, I mean, hydrogen basically is the evolution of energy. I mean, it falls along the same chain of just less C and higher H as you go from wood through charcoal, coal, oil, methane, and hydrogen. All that you're doing finally is to remove the carbon. I'll leave you with a bibliography if people are interested. These are the key papers that you can go and read if you're interested, like I say. But those are probably the best. The Smith paper from 2002 is down here. The rest are all 2020 onwards. But yeah, I'll leave it there and I'll take any questions. Thank you.
You have a question for students?
Oh, student questions.
I thought you had.
Okay, I'll tell you the two student questions, all right, for everybody else, while you think of some questions. Student question number one for the geological table is, what are the circular depressions called that indicate the seepage of natural hydrogen from the Earth's surface? Question two for the engineers, what is the estimated amount of hydrogen that will be used in the world in the next 30 years?
I think you got the prize for them as well.
The prize is a.
You should show the prize first.
Yeah, the prize is a beautiful T-shirt.
All right. Well,
But we'll leave that one. We'll leave that one for later. It can come back.
ใครจะตอบ
I think even professionals would not be able to answer that.
Well, the first question was on the second slide, so.
Looks like nobody can answer. Okay, I think we have.
Sorry, sir. Can you repeat the question?
Okay.
please?
For the geologists, what is the name given to the circular depressions that are seen on the surface of the Earth above hydrogen seepage?
It is a
And for the engineers, what is the estimated amount of hydrogen that the world is going to need to be producing in the next 30 years?
For the first question, I think the answer should be the fairy circle.
Correct.
Come up front. Come forward. Come forward.
ไอ้เหี้ยเอ้ยเราชุดกูก็นอก
Well, I like this. You got a bright coloured shirt on, so you can have another bright coloured one.
Can you quickly introduce yourself? And then your background?
อ๋อ อ๋อ
Sorry.
Good evening, sir. My name is ปิติพงษ์รอดกำเนิด I'm a fourth-year student from Geologic University.
And you are a geologist or engineer?
Geologist.
Ah,
Thank you.
Thank you.
well done.
Thank you.
I hope it fits.
Second question.
Second question, anyone there to answer?
Engineer, anyone? Okay.
So for the second question, I think is it 500,000 tons per year?
That's close enough. It's 500 million tons.
You have the price as well? Okay.
You need to tell people who you are.
Evening, everyone. Good evening, everyone. My name is Jitiwatisi. I am a second year of petroleum engineer at Geologic University. Thank you.
All right, so it's time for the question from professionals. Okay, let me start. My name is Panik from Rula Energy. I understood that, first of all, great presentation, very great knowledge from me. First time on this topic as well. My question is that I think you make such a discovery for the project, but how could you quantify the volume or how much hydrogen in place? Would it be the method would be the same with oil and gas, or what would be the key differences?
Well, since nobody's really done this before, then we're sucking and seeing, so to speak. I mean, the way we've come up with a volume estimate here is to assume, certain different gas compositions, and then we've just basically used Boyle's law to work out, what the compressibility of those gases would be. And so the figure you see, 500 BCF, would be around about 1.1 million tons of hydrogen, if it was 100% hydrogen at that depth. It's a little difficult because no one's done this before.
Any further question?
Hold on. Tam. Here first. Okay.
Hi, sorry, I'm Siri from PTEP, a low carbon business. I'm curious, what is the levelized cost of hydrogen for the natural hydrogen
The normalized cost?
Levelized cost of hydrogen, the unit cost.
Unit cost, I said to you earlier, I mean, natural hydrogen, most of the estimates are less than $1 per kilo.
Per kilo.
And Mali is definitely less than $1 per kilo. In Spain, I can tell you how we did the calculation. We basically know what the volume of the gas is. We run various compositions. We've then assumed a methane development, and we've just increased costs on steel. We've increased costs on facilities. It depends on whether or not you need cryogenic separation if you've got helium. But when you factor all that in and you can bung in some more costs and stack it really highly, then at the wellhead, I think we're still coming in. I think the worst case for us is nearly $1, 80 cents, but most are 50 cents per kilo.
Good evening, Frank Timmons with Tractus. So in the presentation, you intrigued me with a mention of an alternate theory of the formation of Earth, favored by, I guess, originally Soviet scientists. You then further caught my attention when I believe twice you mentioned gas composition for natural hydrogen sources, which included amounts of helium. Mm-hmm. Since helium is an inert gas, I don't know why it would be associated with anything in particular, such as hydrogen, but I'm scratching my head about this alternate Earth theory. Any comments on that? Or?
That's good. We need to remove the little thing there in front of the projector. But no, it's a good comment. I mean, let me explain to you. I mean, I spoke to some people before we started. This project in Spain started as a helium project. And it started as a helium project back in 2017. And that was because I was working on a helium project in the UK, and we were working with the world expert on helium, Professor Chris Ballantyne at University of Oxford. And during the course of that discussion, we were talking about the presence of helium and hydrogen. And Chris, and he's the guru, he's pretty much told me, he said, if you've got hydrogen, if you've got helium, you'll have hydrogen. And I said, well, okay, if you've got hydrogen, will you have helium? And he said, of course, yeah. And of course, I knew about the well with the hydrogen. And so this project started as we're going to look for helium because we know there's hydrogen there. So for whatever reason, the two do seem to go together. Now, one thing I do know is that helium is transported in methane. I don't know if the word is right to use the word soluble, but it can be migrated long distances with methane. But remember, the sources of probably of hydrogen and helium are different from methane. This is if you really want to do some reading, and you're really into this, and I know an engineer, actually, a refinery engineer. I gave this talk in Singapore, and he asked me to send him the book, and he went off and read it, but his wife was Russian. But basically, the real guru of this is Professor Larin, who's an ex-Soviet geologist, scientist, and they did a lot of work on this concept called the hydridic Earth. And as you can see there, the translation, the new geology of our primordially hydrogen-rich planet. And this was translated by an American scientist, Warren Hunt, in about, I think the translation happened about 2002, but then there's a series of other papers. But this is the key one. I've got a copy of this if anybody wants to read it. But it looks nothing like anything we will have seen if you're doing geology. And it's based upon, what happens in, I suppose, other planets in the solar system, in that you start off with hydrogen enrichment and that the hydrogen stays there. And I'm not an expert on this, but essentially on the right here, you basically on the right you see our view of a sort of cut through the Earth, with metals, iron alloys being closer to the center and silicates being towards the outer part of the Earth. And in the hydridic Earth theory, you have metal hydrides that are in the center of the Earth, metals then with dissolved hydrogen, and then you come up into metals, intermediate alloys, silica, magnesium, and silicates are a very thin part. Now, this is still quite thick, yeah? We're talking crustal scale. But basically, it's a big difference from one to the other. I'm led to believe that you can use the same information that we are using to devise this model, i.e. geophysical methods. You can come up with this, is what I've been told, and that book sort of tries to explain that. But if you believe this, it means that the hydrogen emanates from this zone here, the asthenosphere, sorry, up here, and that it just moves through the crust. And you can find it in many, many places. And the former Soviet Union was the only place that they actually went out to try and prove this concept. And they drilled wells in places you wouldn't drill for oil and gas. And if you can remember the slide I showed with all the hydrogen occurrences, you'll have seen that a lot of them are in the former Soviet Union. And that's because they drilled wells where you wouldn't traditionally drill for oil and gas. And so it's tantalizing that, because we haven't drilled in optimum places, it's not like all the hydrogen is in Russia or Eastern Europe. It could be everywhere. It's just that we haven't used a theory like this. But it's quite a challenging book, because if you're a geologist more familiar with the way we look at things, then there's lots of stuff in here which is quite quite difficult to grasp and understand. I don't think he is, but Zgonik, the guy who wrote the paper, Slava, I think witnessed a lecture by him, maybe before he died or passed away, and he's a big believer in there's a huge amount of Russian literature, most of which is not in the Western domain. For instance, the one on potash salts, I tried to get that paper from the Geological Society of London, which normally has everything. No copy. I had a friend, a colleague who lives in Moscow, and he had to go to the National Academy of Sciences to get the paper, and then we got it translated. So there's a lot of literature there which hasn't come into, I'm not decrying it, because science is not like that. Science is science until proven otherwise. But you need to keep an open mind. And there are wells that are being drilled in the United States on the failed rift through Kansas and places like this, which is Slava Zonic's company, are really looking at things like this. And they found hydrogen. They have found a hydrogen, and they flowed hydrogen, but very small amount, and not anything that you'd be excited about. So no one would have thought at all there was any chance of hydrogen there, but they found something, and that work is continuing, and they're using the results to move to wherever they're going to go to next. Thank you.
Good evening. My name is Dr. Chana from SEAPEX Thailand. Everyone maybe have heard about that in the northeastern part of Thailand, we have the big resources of the potash or salt. Is there any study that survey that possible that we can have the natural source of the hydrogen from Thailand in the northeastern part?
Yeah, I think potentially it all depends upon the presence of this, the radioactive elements that are present within it, and but again, not a lot of work has been done. It's mainly in Russian, the ones on the potassium-rich salts. We were very interested in Spain because the salts that we have intersecting around the Bunter are potassium-rich as well. So we were thinking that might have been a source of the hydrogen. But until I think you get samples and you could, do some proper analysis, certainly we haven't done that. But it could be done, and
Okay, one last question.
Hi, good evening. I've been working for a year on a project to produce clear hydrogen, which is one you didn't have in your slide. This is hydrogen from oil reservoirs by injecting an oxygen mixture. In France, where legislation doesn't exist, so I can relate to what you said, it's very difficult to to kick off projects in Europe. There's a lot of energy transition and hydrogen and stuff, but the legislation still has to be written. So that's one comment I wanted to make. The question is regarding the levelized cost of hydrogen you mentioned, 50 cents per kilo is very good compared to other forms of hydrogen. Is that hydrogen with 99+% purity ready for consumption? Like it's been processed, purified at surface?
No, it wouldn't be necessarily fuel cell grade hydrogen. This is something that we're working on at the moment. It's a very good point because
we found that to purify, I think you mentioned 25 to 37% hydrogen.
Mm-hmm.
The break even to make a project work is by having a consumer that wants a hydrogen, so that you don't have to put it in a pipeline. You don't have to compress it. Basically, you need to have like a fertilizer plant is a good example, where you have a well and then you purify the hydrogen by PSA unit or whatever, and then you have a consumer right there.
Yeah,
if you have to liquefy it, track it, then we are in the range of 10 euros per kilo or 20.
No, you're exactly right. I mean, exactly right. I mean, part of the work that we've done as a company is we've got a technical team which has looked in many places in the world, and we do all the technical work. It's like a play map, and then we put a population map over the hydrogen, and we throw out about 80%. I mean, I believe that hydrogen in the middle of nowhere will just be like stranded methane, and because it's even worse. And like you say, it's very important. The project in Spain benefits from Spain's second largest fertilizer plant is 8 kilometers away.
Okay. Same the project I'm working on.
Which is helpful. But you don't know. I mean, the problem is, this is for us. I think you got to think about this. This is a giant science experiment. First of all, can we actually replicate it? Will it work? But you've got to remember the amount of money which is being spent on hydrogen, as you probably know, in the European Union alone is billions. And to test this concept is 12 million euro. And so the argument we've been making with people is, you can either invest 100 million over 10 years and still have a research project which still hasn't got a deliverable, or you can have a failure leg within 3 months that it doesn't work, or it does. And let's face it, there could be, the first one might fail. I mean, just like oil and gas, you just got to have a portfolio, and you need to look in many places. So it's a good question. You're right. Hydrogen, is very difficult to deal with, and until the infrastructure exists to move it around, it's almost valueless.
Thank you.
One of your comments are that I was actually established that you honed in right away that most of the places that have, I guess, true hydrogen assets are outside of Asia. I think everybody in this room can see the picture of the globe with the circle that says more people live inside the circle than outside of it.
Yep.
And I don't think there's one single well inside that circle.
No, you're right. But that's there is potential. I mean, I was in the Philippines 2 weeks ago. Philippines has potential.
That's right.
The Philippines is moving. Philippines is going to get legislation. It's going to happen within the next couple of months. Right, guys? They're energy poor. And think mobile phones. They're not going to put a landline network in. They'll put in they'll just go straight to mobile, and maybe they're going to do that with hydrogen. But they're very excited about it. I wouldn't say that it's 100% the best place, but there's potential. But there's potential in Thailand, and there's potential in Indonesia. You got a lot of collisional margins. You have a lot of plate boundaries. You have a lot of ophiolites or strange rocks like that. But we don't explore for oil and gas in those areas. So, it's a different mindset. And, but hopefully that will happen. Yeah, it's a good point.
All right. That's okay. Thank you very much, Dr. Chris, for such a great talk. And on behalf of SPE Thailand, we'd like to present you the token of appreciation from our big boss, Kun Rono, which is looking for something. What are you looking for? Okay. Our applause, please. Right, it's not over yet. Moving on to our MC for the closing remark.
Well, thank you so much, Dr. Chris, for the excellent presentation. I believe everyone here are inspired about the natural hydrogen. For the closing remark, okay, waiting for the slide. Okay, we still have the lucky draw. It's your last chance to put your name for the lucky draw and put in the pot. And the hotel staff will collect them. For the next meeting next month on the 16th November at here Landmark Hotel, we will have a presentation from, I don't know how to pronounce this, Atkinson Ali, senior analyst from Rystad Energy. The topic about from the group up trend shaping the energy market in the Thailand toward 2030. And we hope to see you all here the next month. And we have completed the SPE Thailand. We have completed the project submission for the SPE Thailand E&P Award for the next year, and the submission will close on February next year, and the event date on September 2024, together with the season opening. And please check the information on the SPE Asia Pacific website. We have the upcoming event and seminar. And this one to promote for the SPWLA event for the next or for this month on the Thursday, the last Thursday of this month on 26th of October. We will have the event at the Jasmine Hotel. And also have the event to call for the APSAC SPWLA Asia Pacific Regional Conference 2024. Please submit your asset as per email, and the deadline for the submission is 29 March next year. And next year we have the event for SPE and IADC Asia Pacific during Technology Conference, and we hold in Bangkok in the August next year. Please, we are calling for the paper, and if you have any presentation, please submit your abstract. And we can keep in touch with our channel. We can go to the spethailand.org, or you can scan on the QR code here in the screen. We have a Facebook page, LinkedIn, and you can connect with us in the Line OA. And the last, for the lucky draw, may I invite Dr. Chris to put a lucky draw for the audience? We have two prizes.
อันนี้ก็ซื้อ2เป็นคู่
โอเค
This is one This is one
ทำอะไร
Oh, this is one of the students
Okay.
from Chulalongkorn University. Where are they? In the back, of course. Kun Pichaya Anchana. I'm not sure if I pronounce the name correctly. Please come forward. Now we have a pillow, so you can have a good sleep after a long talk.
And we have a socket.
That's why we don't do it before. Now, ถ่ายรูป Picture ไหม ช่วยถ่ายทำทุกอย่างที่คนเดียวโอ้ One more
One more.
with the same price. Sleeping pillow and travel adapter. Not sure why these two are related, but try. This is not the another student. Only student in the board. From Geologic University, คุณปิติพงษ์โรจน์กำเนิด is it? Oh, it's the guy. I think he got his lucky share today. Congratulations ครับ That's why George has got more price. Okay, congratulations.
Okay, thank you so much. Last but not least, please give a loud applause for our sponsor for tonight. And thank you so much, and see you next month.
Thank you.
ฉันอยู่มาร์เก็ตติ้งไปแล้ว
Thank you.